Welcome to Train Signal. I'm Chris Bryant, CCIE number 12933, and this is the Network Components video. And as you can see by the topics on the whiteboard, we're going to talk about just about every different kind of device we've got in our network today. Because frankly, as you can see just from this list, we've got a lot of them. There are a few misconceptions about what a couple of them do, and you may not have gotten to work with switches and routers in person yet. So we're not just going to talk about the theory of what the devices do. We're going to actually walk through some processes where the switch builds its layer 2 address table, how the router builds its layer 3 address table, and we're going to draw the lines between what these devices do and what they don't do, because it's equally important to know what something can't do as to what it can do. And speaking of somewhat limited devices, let's segue into a discussion of hubs and repeaters. Now, both of these devices work at the physical layer of the OSI model. They're at layer 1. And as you know, at layer 1, what have we got? We've got ones and we've got zeros. We don't have any frames, we don't have any packets, we don't have any segments. All we have is a stream of ones and zeros going across that wire, because that's the only thing the electric wire understands. So they're not going to do any kind of traffic directing at all. They're not going to do any switching, they're not going to do any routing, they're not going to do any path determination, path filtering, anything like that. The one thing they can do is strengthen the signal. And in another video in this course, we're going to talk quite a bit about segment length maximums with different kinds of cable. And what happens to any electrical signal that travels is it's going to weaken gradually as it gets further and further and further away from the source. It's much like listening to a radio station in your car. And you're driving out of town and you're listening to the radio, and it usually happens during your favorite song. But sooner or later, the signal just keeps weakening and weakening and weakening to the point where it's breaking up. You really can't listen to it anymore. And it may actually start mixing with another radio station in another city because they use the same frequencies. Well, that's called attenuation. It's the gradual weakening of a signal. And what hubs and repeaters can do is take an incoming data signal and make a clean, strong copy of the original. And again, otherwise, this signal would just keep on getting a little weaker and a little weaker until the point where it became unusable. Now, realistically, repeaters are just about extinct in today's networks. They're just about gone. One major problem is they only had one input port and one output port to begin with. So that kind of limits our options right there. And naturally, that meant that we could only regenerate a single data signal. Now, hubs are really just multi-port repeaters. I know you'll hear about smart hubs and that kind of thing, although you don't really even hear about those anymore. But at its base, a hub is a multi-port repeater. And those multiple ports do give them some value in today's networks. By using a hub to connect 4 PCs, as we've done here, we're left with one collision domain. Any data that is sent by any one of these hosts is subject to colliding with data sent by another host. And we've talked about collision domains and broadcast domains in other videos, and we keep revisiting that. But it's so important to remember which devices can break these domains up and which ones can't. Hubs don't break anything up. Repeaters don't break anything up as far as broadcast and collision domains go. Now, using a hub here results in one collision domain, and it also results in one broadcast domain, because a broadcast sent by any of these hosts is going to be heard by every other host, and we really can't do anything about that. That's the default behavior of a switch as well, but as we've discussed in another video, we can use virtual LANs to break up collision domains. So that's really about all there is to say about hubs and repeaters. You know, it's a layer 1 device, doesn't break up a collision domain, doesn't break up a broadcast domain, and their main purpose in today's networks when they are used is to strengthen the signal and avoid attenuation. So having talked about hubs and repeaters long enough, let's take a look at bridges and switches. Bridges and switches both work at the data link layer of the OSI model, which makes them layer 2 devices or L2 devices. And of course, at layer 2, we're concerned with MAC addresses. And both a bridge and a switch will read a MAC address, and they will create a MAC address table. And that's going to allow that device to help send frames to the proper destination in a more efficient manner than just flooding them by just sending them out all ports at all times. And you really see very few bridges in today's networks, especially with the advent of layer 3 switches. And if you're kind of skipping around in the videos a little bit, just to remind you, a layer 3 switch is a switch that is primarily a switch, but it has routing capabilities as well. So bridges still can serve a purpose, though. Theoretically, they can connect networks using different media. That is, if we had token ring segment on one side of the bridge and an Ethernet segment on the other side. They're protocol independent or protocol ignorant, depending on whose documentation you're reading. And I will tell you that sounds great, but it's my experience that in the real world that doesn't always work terribly well, and it can be a very difficult configuration to get to work. So while theoretically, again, bridges can connect networks using different media, in the real world that doesn't always work terribly well. Bridges also will not forward data across the bridge, so to speak, from one segment to another unless the destination address is valid and actually requires it. And I want to show you what a bridge looks like in network documentation, and that's the universal symbol for a bridge. You should be prepared to see that on any certification exam and know what those devices are connected to. And you've already seen in a couple of other places that this is what a switch looks like. You should certainly be familiar with that by this point. And it's not that bridges are really bad at their job or evil or anything like that. It's just that switches, frankly, are better. They can operate at higher speeds. They do offer a great many more options. If you go out to Cisco's website, look in the documentation, and just look at what a regular switch can do, not even a layer 3 switch, you've got a tremendous number of features that you can use, and bridges are not going to offer all of those. And of course, as I've mentioned a couple times here already, switches can perform routing as well as switching if it's a layer 3 switch. On an exam, if they just talk about a switch, they're talking about a pure layer 2 switch. Just as if you're reading documentation, if it just says switch, it's a layer 2 switch. Those switches, those layer 3 switches used to be called routers, but you really don't hear that term very often anymore. It's combination bridge router, but in case someone mentions a router, I want you to know what they're talking about. Now, there are two rather confusing facts regarding switches that I want to mention here again that I did mention in another video as well. That MAC addresses are called physical addresses also because they physically exist on the NIC. They're burned in, which gives them another name, burned in address. But whether it's a physical address, a MAC address, burned in address, it's still a layer 2 address. Physical addresses have nothing to do with the physical layer of the OSI model. Now, just as you heard several different names for MAC addresses earlier in the course, you'll also hear the MAC address table called several different things. It could be called a MAC address table, a bridging table, a switching table, a physical address table, or a layer 2 address table. They're all the same thing. Bridging table you don't hear as much as you used to anymore because frankly bridges are just about gone out of today's networks. But you'll still hear it on occasion. So whether it's a MAC address table, bridging table, switching table, I don't care. It is a MAC address table. They are all the same things. But no matter what you call it, you need to know how switches build that table and how they use it to determine the appropriate action to take with an incoming frame. Now, the example we're going to walk through in a moment is an illustration of how a switch builds a MAC address table dynamically. You can make static entries in a MAC address table. You really don't want to do that. This is one of those situations. Dynamic is much better than static because as hosts are moved around, if we're using dynamic learning on the switch, they'll learn the new location of the PCs, of the hosts. But if you do it statically, Then you got to go to the switch every single time a host ever gets moved or changed and change configuration. And frankly, you and I both have better things to do. Before we take a look at the example, just want to remind you that by default, both bridges and switches forward broadcasts. We're going to use 4 hosts for this example, and for simplicity's sake, what we're going to do is have each host's MAC address be the host name repeated 12 times, A, B, 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 and so forth, so we don't have to keep putting them up on the board. Also note that host A and host B are actually found off the same switch port. They're on a shared segment, and that just might become a point of contention here in just a moment. Now, when a switch is first booted up, it has absolutely no entries in its MAC address table. And one interesting fact is that the table is actually going to be built from the source MAC address of an incoming frame. Because what you might think is when a frame comes into the switch, the first thing it looks at is the destination MAC address, but that's not true. It looks at the source because that's how it builds its dynamic switching table. So we just booted the switch up. We're assuming the switch does not know off what port A, B, C, or D can be found. And what we're going to do first is assume that A is sending a frame to host C. And here comes the incoming frame, and you can see I put the source MAC destination in the arrow of all A's to indicate where that's coming from. Again, the first action the switch will take is to examine the source address of that frame. If the switch has an entry for that source MAC already, and the entry matches the port it came in on, then the switching process continues. But that's what I meant a few minutes ago when I mentioned that when you let the switch learn addresses dynamically, it can learn new locations dynamically as well. If we took host A and put it into port 20 this afternoon after the switch learned it's off port 1, when the switch gets an incoming frame on port 20 from that same MAC address, it's going to say, hey, wait a minute, something's changed here. They moved, that host has moved. So I'm going to age out the old entry and put in port 20. So again, dynamic is really the way you want to go here. If the switch does not have an entry in its MAC table for this particular source MAC address, it'll make one. And you see there on the right, I've put one in there simulating the MAC table, and it's saying, okay, I know that the source MAC or the MAC address, all A's, is found off port 1. So the switch has no entry for the MAC address, it makes one, and now the switch has to make a decision about what to do with that frame. And the decision is the filter, forward, or flood decision. By filtered, I simply mean the frame will be dropped. Forwarded means it's going to be sent out the correct port for the destination MAC address, and that is unicast out that port. Or flooded, which is sending it out all ports except the one it came in on. Sounds like a broadcast, right? I mean, that's what it is. It's going to send it out every port except the one it came in on. We don't get to say never very often in networking, but there's no reason for a frame to ever be sent out the same port it came in on. It literally cannot happen. Now, here the switch has no entry for host C, the all C's MAC address. That's where that frame is actually going. So it can't be forwarded. So what happens is the frame is flooded. It's going to be sent out, a copy of the frame is going to be sent out every switch port except the one it came in on. Because again, an important bit of networking theory is that a frame will never be sent out the same switch port it came in on. Now we have to consider what's going to happen when host C responds to host A. Now we've got an incoming frame from host C to host A. And the source MAC address of this frame is the all C's address, which we're using for host C. Now the switch first will look to see if it has an entry for the source, which is all C's, and it doesn't. So it makes an entry, and you see I put a second entry there for the MAC table, that the all C's MAC address is found off port 2. So now it'll look at the destination, and it's got to make the flood, filter, or forward decision. And this time, the frame will simply be forwarded out port 1 because the switch does have an entry for the destination of that frame, the all A's address. So we've already looked at a situation where we have a flood and where we have a forward, and now you might be wondering, well, under what circumstances are we going to see a frame filtered? And I'm going to leave this particular exhibit up here. We're going to keep using this one. A switch is going to, like I said, forward a frame, or filter a frame, I should say, when it realizes that both the source and destination are found off the same switch port. So let's assume at this point that all of the hosts on this network have sent data, that the switch knows where all the devices are, and host B sends data to host A, or host A sends it to host B. Well, this being a broadcast segment, a shared segment, the switch will see that frame, and it's going to see the data come in on the switch port and look at both the source and destination address, just the way we talked about it in the previous two examples. And as soon as the switch sees that both the source and destination MAC addresses are located off port 1, the switch drops the frame, because the switch knows, okay, that being a shared segment, B is going to see it anyway. I don't need to send a copy of it. I can see in my MAC table that both A and B are found off the same port. Now again, as we get away from shared segments and we get back to having the hosts in their own dedicated switch ports, which is what you see in most networks today, you don't have that much filtering going on. But you need to know when a frame is filtered, and a frame is filtered when a source and destination are found off of the same switch port. And that drawing we looked at earlier, we're going to go back to that for a moment. And this is a much more typical network where we have all the devices that have their own switch port. And this is an ideal configuration because here we have 4 separate collision domains, where each host is connected to its own dedicated switch port. They can all send data with no danger of collisions. Now we still have one broadcast domain though, because a switch forwards a broadcast by default. And the only device that we're going to talk about here in this video that doesn't forward broadcast by default is a router. But keep in mind that even though a switch will forward broadcast by default, when we configure VLANs, that cuts down on the amount of broadcast traffic in our network, because when a host in a certain VLAN sends a broadcast, only the other hosts in that same VLAN will receive it. The routers run at layer 3 of the OSI model, and their basic operation, well, it's to route. It's to route data packets and examine their own routing tables to see where to send the packet next. Now, again, routers are at layer 3 of the OSI model, and they can be configured with static routes, but again, if we can have things happen dynamically, we'd like them to happen dynamically. I'm not against the use of a static route once in a while, but usually you can get everything you need done in a dynamic fashion by using a routing protocol. And I put a couple on here for you. I doubt very seriously you even see these mentioned on Network Plus, and you'll definitely have plenty of time to learn about them in later studies, especially for the CCNA. But it's good stuff to know if you happen to have heard these terms around the server room. RIP is the Routing Information Protocol. OSPF is Open Shortest Path First, which is always a good idea. EIGRP is the Enhanced Interior Gateway Routing Protocol. BGP is Border Gateway Protocol. And again, you'll learn a lot more about these individual protocols and what they do should you choose to pursue your CCNA. But these protocols are very different from each other. Believe me when I say that. The more you learn about them, the more you see how different they are. But the routing process itself always stays the same. And what we're going to do here is take a look at the routing process. You can see what's going on a router by router basis. And let's start with this exhibit. In this diagram, there's a PC on the 10.0.0.0/8 network, another PC on another network 20.0.0/8, and you can see their individual IP addresses there next to the host devices. And in this example that we're going to walk through, the PC in this situation, the top one, wants to send data to 21.1.2, but has no idea where that host is, because it's not connected to the 20.0.0.0 network, so it can't know where it is. The host itself is not going to be running a routing protocol. So in this case, the PC should be configured to use the router interface on its segment as its default gateway. And I'm going to give you several definitions for gateway here in a few moments, because it's a widely used term and it can mean a lot of different things. But default gateway is basically, there's where I'm going to send this data if I don't have any other idea where to send it. It's a gateway of last resort. It is the default gateway. You may have actually configured that on a PC, and also that's a piece of information that DHCP can assign to a workstation. In addition to the IP address and the mask and the location of the DNS servers, everything we talked about in the routing, in the network protocol section, then we can also tell the PC, here's your default gateway. So in this particular case, the PC would send the data to the router and just hope that the router knows how to get the data there to begin with. And if it does, which of course here it's connected to both segments, so it will, the PC at 10.1.1.2 will send the data to the router. The router will look in its routing table and see that it is connected to the network 20.0.0.0. So it says, okay, if I want to get it to that particular host, I need to send it out my interface that's on the 20.0.0.0 network. That is a directly connected network, and that's the only kind of network that the router does not have to learn about, either statically or through a dynamic routing protocol. As soon as you open that interface up and give it an IP address, it sees, okay, I'm already directly connected to that. Again, routers do not depend on routing protocols to tell them about networks that are directly connected, and so this particular routing would not be a problem. As you can see here, I've illustrated a little further and taken the one PC out, but you can see the incoming packet coming into the router on Ethernet 0, and this particular router has two Ethernet ports, Ethernet 0 and Ethernet 1, and it sees the incoming packet IP destination as 21.1.2/8. It's going to look in its routing table and say, okay, I'm connected to that network, so I know if I send it out E1, then it's going to get where it needs to go. Now, routing protocols become necessary, though, very quickly, because if a router isn't directly connected to a network, we've got to tell the router somehow this is where to send data to get it to network X. And we can do that statically or dynamically, and again, you'll learn more about that later in your networking studies. But let's take a look at an example where a routing protocol or a static route would be necessary. I've taken the sending host out of the diagram here just to make it a little more clear, but in this scenario, the first router is directly connected to networks 10 and 20. And that particular router is receiving a packet destined for the host you see at the bottom, 30.1.1.2. Well, the router is going to look in its routing table and see that it has nowhere to send that. It doesn't even know of the existence of that network, network 30. It doesn't have the faintest idea. So what it's going to do, unfortunately, is drop the packet because it has no idea what to do with it. Now, what we could do with that router is give it a static route and say, okay, if you send it to this other router that's on the other side of network 20, then that router could get it there because it's directly connected. We could also be running a dynamic routing protocol, and that would allow the router, the top router, the one that's receiving the packet in the diagram, to say, okay, I know where network 30 is. If I send it out this interface, then it's going to get there. So that's how the routing packet delivery process works. As long as the networks in question are directly connected, there's no routing protocol needed. But as soon as they're not directly connected, and of course a router can only be directly connected to so many networks, then it's just going to drop the packet, and we've either got to tell it statically how to get it there, or we've got to configure a routing protocol. I mentioned the term default gateway in the few minutes ago, and that is where a PC is going to send data if it has absolutely no idea where else to send it. A router can be configured with a gateway of last resort, and that's a downstream router to send data to, again, if the router doesn't have a good idea or a better idea of where to send it. But there's another term, a more broad term, gateway, that does not describe a specific piece of hardware. It can describe hardware, it can describe a router, but it is not a specific piece of equipment. Gateway has at least 4 different meanings in networking, and don't get too frazzled thinking, oh man, there's something else to memorize, because they're all kind of related. You'll see one point between all the definitions here I'm going to give you that relate. And you're going to hear it a lot, and people use it a lot. Sometimes they use it correctly, and sometimes they don't. But I just want to give you these 4 so you'll know what they're talking about, hopefully. First, a gateway can be considered to be a device that connects separate networks, such as the router that we just looked at. If you've got a device connecting 2 separate networks, that is a gateway. Another device, another definition for gateway, is a device that connects networks using different protocols that allow them to communicate. Because those, let's take for example the routing protocols I showed you earlier. Those routing protocols are all different languages as far as the router is concerned. If you have RIP and EIGRP running on the same router, those 2 processes do not understand each other. If we want to make them understand each other, we can, but we've got to do some configuration there. So a gateway is, again, a device connecting networks using different protocols, which allows them to communicate. Another term that gateway matches up with, another definition I should say, it's a device that allows networking equipment created by one vendor to communicate successfully with another vendor's equipment. Because I know this is going to shock you if you're not active in networking right now, but vendor devices from different vendors, they don't always play well together. Trying to get a router from one company to talk to a router made by another company can be a little challenging. So we need a gateway device involved there somewhere. Finally, a definition for gateway you may be more familiar with is it's a device that translates messages from one vendor software program to a format that's understood by another vendor's software that does much the same thing. And one application type that I can tell you uses gateways often is email, because as offices, or I should say companies, get larger, as they merge, I've been involved in companies where one side used Microsoft Exchange and the other side used Lotus Notes, and they had to get the 2 to communicate, and a gateway was necessary there. Now again, a default gateway, that's where a host sends packets when there is no specific idea as to where to send it. And in the PCs that we looked at in the previous drawing, they were using a router as their default gateway. But you know, for all the stuff, the work that we've been talking about, you know, switches, hubs, routers, repeaters, and now different types of gateways, the PC's got to be able to send data in the first place. And that ability all starts with the NIC, or the network interface card. I've got a couple notes here on the whiteboard about NICs, but we're going to add to those here in just a moment. Now the NIC is a physical device or card, and that's just a term we use in networking. Something kind of looks like a card, it's flat, fits in your hand, and it slides right into the PC or the host device. This is the device that actually gives a PC or a host device a physical connection to the network. And most NICs these days are internal. When you buy a PC off the shelf, you're going to have the NIC already in the PC, and you just need to connect your cable to it, to your cable modem at home, and you're ready to get on the net. Again, it can be removed and replaced with a different NIC, and network interface cards can be external devices, but generally today they're internal. And I mentioned here to take your time when purchasing a NIC and when installing it. Most issues involving network cards occur before the device is even added to the network. And that may sound odd, and it's because the purchaser didn't do their research. You know, bought the card a little quick, it doesn't have the capabilities they thought it did, Occasionally, that's because the vendor documentation can be a little difficult to read at times, but most NIC issues actually come up simply because the person buying the card bought the wrong one. Happens to almost everybody. I've done it before, and you get it, it's like, oh, this isn't quite what I needed. But now the documentation's better, and it's easier to make the correct decision. All NICs are not created equal. If you try to take a token ring NIC and put it in a PC, put it on an Ethernet network, it's not going to work. Practically guarantee it. Speed types, speed capabilities vary, connector types vary. Don't just assume that any particular NIC is going to fit your device and give you the results that you want. If you go out to the vendor's website, spend a few minutes looking up the specs or specifications for the NIC, it can save you a lot of trouble once you get it. A well-placed phone call to tech support doesn't hurt either. Don't be afraid to call the vendor. Now, when I talk about take your time when installing it, first off, make sure the device itself is off when you're putting a NIC in, whether you're swapping one out. Make sure you're properly grounded as well, because there's a grounding strap that actually used to come with NICs. I don't see that as often anymore. But any good server room, and even a bad one, should have some grounding wires, the grounding straps. And you basically connect yourself to the PC, and what you're doing is preventing the generation of static electricity. And occasionally I'll see somebody say, oh, well, it's not that big a deal, and I don't know where the strap is. Come on, we got to hurry up. And they shift their feet or something, or they move their hand across the back of the PC, they create a little static, and they fry the card. It does happen. So make sure that you are properly grounded. Now, your NIC will require a download of the appropriate driver. And if you're new to this part, drivers sound like something physical, right? But they're not. A driver is only a software file that a particular device needs in order for the NIC to work correctly. And NICs are not the only thing that need drivers, right? The big thing is printers. If you get a new printer, you've got to have the drivers for it. And where in the old days of floppy drives, when you bought something like a NIC or you bought a printer, come with a floppy and had the files already on it. Well, today, for two reasons. First off, to reduce costs. Manufacturers do not always include a CD that's going to have the drivers that you need. They want you to go to their website and download them. That actually works for us in one way, because we're getting the latest drivers. We don't have to worry that these drivers are 6 months old and there's been an update, but we don't know about it. But it does lend itself to an occasional catch-22 for NICs. And you might get caught in a situation where, well, if I don't have this on the network yet, and I don't have it on the internet yet, how am I supposed to get out to your website and download the driver to make it work? And if your host doesn't have any network connectivity, what you'll probably have to do is download the drivers to a host that does. And you simply copy the files to CD. If you're working with an older device, you may be able to put it on a floppy, but you probably have to burn it to CD these days, and then install the drivers from CD. So you're not the first person to say, hey, if I need NIC drivers and I have to download them, how can I download them when I can't get on the network yet because my NIC isn't working? Now, the typical NIC has one green light and one amber light. And depending on whether the host has network connectivity or not, the lights will be solid, flashing, or out. And sometimes flashing is good and sometimes it's not. I put a little bit of that on the whiteboard, but let's talk about that for a minute. A solid green light is good because that indicates that you have connectivity. It's generally referred to as a link light. And within a few seconds of plugging that in, you should see the light go green if all is well. If after about 20 seconds max you don't see a green light, there's a problem somewhere. Now that light should stay a solid green. If you see it flashing green, that's a sign of what we call intermittent connectivity. And that's a fancy way of saying 1 second the PC is on the network and the next minute it's not. And you can get that, how you detect it is when you get a user who says, well, I was doing something on the network and I got cut off, and then they say it again later, but you're visiting their workstation and everything looks fine to you. Well, go under there, under the desk, wherever the PC is, and check the back of it and see if you see any flashing of that green light. Because if the green light's flashing, either the NIC or the cable attached to the NIC is going bad. Now, flashing amber lights are actually normal because what happens, that is indicating a collision. And we've talked about collisions quite a bit in this course. They're not unavoidable. They're going to happen. They're actually normal. And even on a very healthy network, you're going to see that flash once in a while. But if it looks solid, if it's flashing to the point where it looks like a solid amber light, you have a real problem. And you need to look into that. But that's a collision issue. And you can see these lights on your own at home if you've got an internet connection. And you just go to your PC, and right next to where the cable from your cable modem or whatever kind of modem you have connects to the host, you're going to see a green light and an amber light, so you can actually see these for yourself. On occasion, you're going to have a PC that does lose connectivity to the network. And one thing I'll mention again in the troubleshooting video, but I want to mention it to you here, it is a mantra of mine that you always start network troubleshooting at the physical layer of the OSI model. And in a workstation, that's going to mean checking the NIC and checking the cable. If you suspect one of those things, one of those components is bad, personally, I would swap the cable out first. Two reasons. First, cables seem to go bad a little quicker than a NIC does. And also, it's usually easier to swap the cable out. And if that is the case, then you're okay now. If the cable is not bad, then you have eliminated that as a possible cause. That's really up to you. But again, if you swap NICs and you still can't get the PC on the network, I would then try a new cable at that point. But always start your troubleshooting at the physical layer with that cable and with that NIC. If you think there's a problem, swap one out. If that resolves the problem, great. If it doesn't, try swapping the other device out. One networking device that may be the first networking device you ever worked with, and it was for me, is a modem. And that's a modulator demodulator. And it's, like I said, much more commonly known as a modem. It is the device that allows a host to connect to its ISP, the Internet Service Provider, which in turn allows Internet access. The modulation part of this occurs when we take the digital data and translate it into analog format, because that allows it to be sent across a telephone wire. Now, at the other end, it's got to be translated back, and that's the demodulation. The analog signal is put back into its original digital format at the remote end of a connection. And the illustration I've got for you here, that's obviously an external modem, but a modem can be internal or external. Now, as modems become less and less popular, I see them built into fewer PCs. You know, they used to be a big deal when you bought a brand new PC. It's like, does it have a modem in it? And, 56K modem was a big deal back then when we rode our dinosaurs back and forth to work. But now we've got a problem with a basic modem because it ties up the entire phone line. And, of course, that leads into arguments among family members and former friends about phone usage versus internet usage. Get off the phone, I want to use the net. Get off the net, I want to use the phone. Thankfully, we've got two other modem types now that help us get away from that argument, because it makes it possible for homes to have simultaneous internet and phone line access. Cable modems actually use part of the cable television bandwidth to allow internet access, while digital subscriber line modems, or DSL modems, use the PSTN, the Public Switched Telephone Network. Basically, a home DSL user's connection to the internet uses part of your pre-existing telephone line, but it does not tie up the phone. And both cable and DSL modems use splitters to accomplish this, because what you're doing really is splitting the bandwidth. A CSU-DSU is a channel service unit, data service unit, and it's found in the same points, the physical points in a network, as a modem might be, but it does not have anything to do with modulation or demodulation. A CSU-DSU is a device that allows a router to connect to a high-speed line, and here we're talking about a T1 line that runs at 1544 kbps. And it can be as small as a modem, it can be much larger, and it does work at layer 1 of the OSI model. Firewalls, very important device in today's networks. because a firewall is your basic protection against internet-based attackers. And a firewall is a physical device of some kind that filters packets that are heading for your PC, and they can also filter outgoing packets, and often do. Now, these filters are set to block attempts to harm your PC in some way. I have incoming packets here, but again, firewalls can and do filter outgoing packets as well, which is something you've got to be aware of when you install a new firewall. Now, the firewall that you see in the illustration here, that's generally where you're going to see them in networks, between the inside network and the end users and the internet. You know, if you're expecting an incoming email attachment and you don't get it, the firewall may well be what removed it. And you also have the option of notifying the sender as to whether as to the removal of that attachment and that it was not delivered. Occasionally, when I send an attachment to someone, I'll get an email in about 30 seconds that says, "Hey, there was an attachment. We stripped it off and went ahead and sent the email." A lot of firewalls don't even do that. They don't even notify a potential attacker, "Hey, we didn't send the attachment." They just strip it off, or they delete the entire mail. Because many companies now choose not to allow any incoming attachments at all, because it only takes one person to open an attachment and unleash a virus on the network. We will talk about that a bit in the antivirus video as well, but never take it for granted that our end users are never going to open a firewall, open an attachment. Because as well as so many people are educated about that now, they'll say, "Oh, you know, this is a smiley cursor," or "this is a free calendar," or something like that, and bam, all of a sudden you've got a virus all over your network. Firewalls aren't limited, though, to filtering messages that have attachments. We can configure a firewall to block certain kinds of outgoing connection attempts as well. And a lot of firewalls do all that by default. They block almost every port under the sun. What happened to me recently is my internet service provider that takes care of my rack rentals, they had to come in and put in a new router and a new firewall, and they could ping the devices, and they said, "Okay, you know, let's go ahead and leave." And I said, "Wait a minute, let's try to telnet to them first, because that's what my customers do and my students do." And I could not telnet to them. And what they had to do was open port 23 on their firewall for incoming and outgoing connections to allow a telnet connection. That's referred to sometimes as punching a hole in the firewall. You'll hear that term sometimes. "Well, we need to punch a hole in it." Well, what they mean is we got to open a port up to let so-and-so work. You know, whether it's telnet and especially email, that's the big one that tends to get forgotten. But again, we're not limited to that either. We can remove incoming attachments. We can block traffic by IP address as it comes in. We can prevent certain kinds of outgoing connection attempts. But the three most common ways or values used to filter traffic, the first one is by protocol. We could just say, don't allow any IPX traffic. Don't allow any TCP traffic. You're probably not going to say that one, but you could if you wanted to. Source IP address. That's where we can write a rule for the firewall that says something like, don't allow any traffic from network 172.10.10 to enter our network. You know, don't allow that. We could also filter by firewall by port number, and that's very common. As I just mentioned, if you block port 23 with the firewall, you're preventing anyone from even making a telnet attempt at a router. And maybe they don't know the password, but maybe for security reasons, you don't even want anybody to be able to attempt it. So you can block port 23. And again, when new firewalls are put in, it is really easy to forget to open a certain port or to shut a certain port. So I have put a couple of common firewall-related issues here on the whiteboard for you. The first two are beyond common. Either the users can't receive email or they can't send email. If they can't receive it, you better make sure the incoming POP3 port 110 is open. If they can't send it, you better make sure that outgoing SMT port 25 is open. Typically, those two ports, and perhaps even the IMAP4 port, are just left open incoming and outgoing. But you don't have to do that technically. The other one, if you want to block web access, that's not as popular as it used to be because so many applications are web-based today. It's not really practical to block web access for an entire building. But if you wanted to do that, or you were commanded to do that, you could do it simply by block outgoing port 80. So again, that's where the port numbers come in. You know, we discussed that. Well, do I have to really know all these port numbers? When it comes to firewalls, yes, you do. You need to know the port numbers. So when your users report certain issues to you, or hopefully you're nailing them in advance, you're being proactive, that's how you're going to filter, is by port number. Earlier in the course, we talked about proxy ARP, and because of that, or even before that, you may be familiar with proxy voting or voting by proxy, where a trusted party casts a vote on behalf of someone who can't be there in person. And that's kind of what happens in proxy ARP, and that's also kind of what a proxy server does for our network. Proxy servers are sometimes referred to simply as proxies, and they're often used to cache web pages and files, much like we see here. This allows a local host to access the page much more quickly than if the host actually had to get the page from the actual web server, because the proxy server is going to be local to the host, where the web server most likely is going to be on an external network. Now, if the proxy server does not have a copy of the requested page, and here I just call it focus.com/focus.html. If the proxy server doesn't have a copy of that particular page, it's going to go out and get one, and then give a copy of the page to the requester, and then store a copy in its cache to fill future requests. Here's an illustration of that process. And again, the host asks the proxy server for it, proxy server doesn't have it, proxy server goes out and asks the web server for it, gets it, then sends a copy to the requester, and stores a copy in its cache. And note, you know, with the web server there, we've got a globe there as an icon next to the web server, but it's interesting that we have the same symbol that we saw for a firewall actually attached to the proxy server. And we're going to talk about that in just a moment. But proxy servers can also be used to run network address translation. We talked about how the only device to this point that we knew could run NAT would be a router. Switches can't run it, hubs can't run it, certainly a repeater cannot run it. But a proxy server can also be used to run NAT. And what happens is the NAT connection is actually redirected to the proxy server when the client's browser uses the NAT process to get a page. This redirection is referred to as an intercepting proxy. I always thought that was a very interesting term, but that's really what's going on, as I say in the third point there under proxy servers. When the client's browser uses NAT to reach the NAT, the connection is redirected to the proxy server, and that is an intercepting proxy. Now again, I bring your attention to that firewall symbol next to the proxy server. And that's not a universal drawing, a universal representation of a proxy server, but you do see it this way in a lot of network documentation, which is why I wanted to show it to you this way. Proxy servers do serve as a kind of firewall, because packet filtering of a kind is really performed on a proxy server, and that's what a firewall really is. It's packet filtering on one criteria or another. And also, when you run NAT on a proxy server, you're hiding the internal IP addresses, the private IP addresses if you're using those, which protects the internal network's privacy. So again, there's another example of how a proxy server serves as a firewall. If it's running NAT, it prevents outside hosts from even knowing what inside network numbers you're using. And while we're discussing NAT, I want to bring up a big point of discussion quickly here about IP security or IPsec and NAT. And in theory, IPsec and NAT aren't compatible. And I'll mention this again in the security video, but in reality, that's not really the case, because NAT is so popular that we can't just throw it out because now we're using IPsec. And the method of getting them to work together differs between vendors. Boy, does it ever. But if you do a Google search or use your favorite search engine on the terms NAT, incompatible, IPsec, you're going to get some links to some very interesting reading. And to sum up, and I wanted to mention that here since we're talking about NAT again, theoretically IPsec and NAT cannot coexist, but in reality they indeed can. Now I'll actually put those terms here on the whiteboard in case you want to look those up on an engine. It corrected my typing there to a capital letter. That's why we got the blue underscore, but don't worry about that. There we go. NAT, IP compatible, and IPsec. If you search on those terms, you'll come to some pretty interesting links to read about how we're getting these two things to work together. But in theory, NAT and IPsec don't play well together at all. We're going to wrap up this discussion of all these networking devices in a moment. We are going to have a review of all this because there's quite a bit of information in this particular video. But I want to talk about one more little piece of equipment that gets left out of a lot of discussions, that if you don't have it in the right place, you're not going to have connectivity. That's called a transceiver. And it's just a tiny little rectangular metal box. And it'll actually fit right in the palm of your hand. And this tiny device does a great big job. Because what transceivers do is they allow network devices to connect to a media type that they were not originally connected or designed for. And the main use of a transceiver is to allow a device to be connected to an AUI port. It's an attachment unit interface port. Now, a lot of ports you see on Cisco routers that are referred to as Ethernet ports are not pure Ethernet ports, they're AUI ports. And the difference, don't worry about that right now, it's way beyond the scope of what we're talking about. But what I'm saying is, you're not going to be able to take an RJ45 connector, the little snap connector, and snap it into an AUI port, because the AUI port is DB15. It's got 15 little pins in it. And you sit there and try to plug that in, you're going to be there a really long time. Well, what you do is you use a transceiver as the middle device here, a gateway, if you will. It's going to allow these two devices to communicate. Simply take the RJ45 cable, snap it into one end of the transceiver, and then just connect the transceiver itself to the router, and you're ready to go. And don't know if you'll see anything about that on Network Plus, but in case you hear the word transceiver, I want you to know what we use it for in a routing room. And we've covered a lot of ground here as far as our router rooms go and our server rooms. Hubs, bridges, repeaters, gateways, modems, CSUs, DSUs, firewalls, and some other items. So what we're going to do here is take a few minutes to review the high points of these, and then we'll wrap it up. We're going to take a review here now of the different networking devices that we talked about in this section, because the differences are very stark. I'm sure you're going to see a lot of this on your Network Plus exam, and obviously to work in real-world networks, you've got to know this material too. So let's take an overview of what we talked about in this video, and we'll start with hubs and repeaters. Hubs and repeaters are layer 1 devices, physical layer devices, and they don't have anything to do with collision or broadcast domains as far as breaking them up. They don't have anything to do with switching traffic, routing traffic. They don't read addresses. They don't do any of that. Their main purpose in life is to prevent attenuation, which is the gradual weakening of an electrical signal. Back when hubs were a little more popular and switches were still really expensive, they used to market hubs as smarter hubs, that kind of thing. And they would have some more advanced features, but theoretically and basically, when you boil it all down, a hub is a multi-port repeater. That's really all it is. For bridges and switches, they both work at the data link layer of the OSI model, so we're looking at layer 2 here, and they both deal with MAC addresses. Bridges are really pretty much gone now, because switches, frankly, are so inexpensive and offer more features, but they still have some good uses. Bridges can connect segments using different media and allow them to communicate. Again, theoretically, that sounds great. In the real world, I'm telling you, when you start bridging and trying to get Ethernet and token ring to talk to each other, it can be very difficult. So again, if you've got that situation, you may want to look at some other fixes for it. Bridges don't send data over the bridge, so to speak, or to the other segment unless the destination address is considered valid by that bridge. And we looked at how switches build their MAC address tables, and they do that by examining the source MAC address. And once they do that, they can make an entry for that source if they need to in their MAC address table, and then they have to decide whether to forward, filter, or flood that particular frame. And remember, forward is just another way of saying unicast. That means that it's being forwarded out one port and one port only because the switch knows where to find the destination. If the switch sees that the source and destination MAC addresses are both off the same port, it will filter the frame or just drop it. And finally, the frame will be flooded if the destination MAC address is unknown by the switch. And by flooding, we mean that it is sent out every port except the one it came in on, because with switches, under no circumstances will a frame be sent out the same port it came in on. Routers. Oh, it looks so simple here, you know, with 3 lines and that's it for routers. They operate at layer 3 of the OSI model, the network layer. And they run routing protocols such as RIP and EIGRP to discover routes. And we looked at a sample, or actually 2 examples, where one time the router was routing a packet to a directly connected network, so it did not need a static route or a default gateway, a gateway of last resort, and it didn't need a routing protocol. But that's not usually going to be the case. Usually it needs to get data to a network that is not directly connected, and under those circumstances, either a dynamic routing protocol such as RIP, EIGRP, OSPF must be running, or we have to put a static route on the router. And a host PC is usually going to set its default gateway to the IP address configured on the nearest router interface. With gateways, we talked about really 4 different ways of looking at a gateway, 4 different definitions, but they all kind of related because it serves as almost a translator. And if you think about it this way, if you had to boil the gateway definition down to 1, I personally would say that it's any device that allows communication between hardware or software that could not otherwise take place. And for example, if we are looking at 2 email programs, you know, Lotus and Microsoft Outlook, anything like that, or excuse me, Exchange, then we've got to have some kind of intercommunication between the 2, but they're not going to understand each other. So we have to have some kind of gateway. We have 2 routing protocols running on the same router. They're not going to exchange information all by themselves. We've got to make them exchange information, and that actually makes that router a gateway. So gateway is more of a description of a device than a specific networking device. A default gateway is where a host sends data if that host has no specific destination for that data. As we just mentioned, a typical PC is going to have a router interface IP address as the default gateway. NICs can be internal or external, but we got to have them. You need to do your research before purchasing, not only to make sure that it's the correct media, but also the right speed, the right specifications for what you're attempting to connect this NIC to. Make sure you're grounded when installing a NIC. Don't be lazy. Don't be one of these people who can't be bothered to walk across the room and get a grounding strap, and then they fry a NIC, and yes, I have seen that before. You don't want to be one of those people. You will need drivers for a new NIC, and I want to mention to you, on occasion when you see a problem and you think it's with a network interface card, try downloading a new set of drivers. You know, delete the ones off the PC that are there now and then install new drivers. Now you need to find the new drivers before you delete the old ones. But a driver, like any other file, can be corrupted over time. And if the drivers are corrupt, the device may no longer function correctly. And occasionally, if you've got a device that you just can't get running the way you want to get it running, try putting new drivers on. You'd be surprised how often that works. Just an extra tip there. For our lights, our green light is the link light. It should be solid. If we see it flashing green, we have intermittent connectivity, which means sometimes we're on the network, sometimes we're not. If you see no light, then you really have a problem because you have no connectivity to the network at all, and either the NIC or the cable is off. For amber lights, that amber light indicates collisions, and it's going to blink when collisions occur. Now, seeing some blinking on there is actually normal. Even a healthy network is going to have some collisions. But if it's blinking so fast that it looks solid, then you've got a problem. So we are looking for a blinking amber light. Modems. When we send data across the telephone line, we've got to take it from digital format and translate it to analog. And then at the other end, once it's to the ISP, we've got to take it from analog format and turn it back into digital format. So the modulation takes place when the data is translated from digital to analog, and then it is demodulated, taken from analog and put back into digital format. In the bad old days of modems, and they are still out there, we have to use them once in a while, a modem will tie up the phone line if you're using it at home. And now there are two different kinds of modems that help us get around that. Cable modems use part of the cable TV channel to allow internet access. And by cable TV channel, I mean a channel inside the cable, not a channel on the television. And DSL modems actually allow you to use the PSTN, the public switch telephone network, to allow internet access. So what you're doing really is splitting this bandwidth a little bit between what you would normally use it for and then internet access. And that's a good way to remember that both cable modems and DSL modems require a splitter to allow this type of internet access. I added a line here about CSU, DSU. We talked about that briefly. That's the device that connects a router to a high-speed line, such as a T1. Some CSU, DSUs you see will just be the size of a modem. You can hold them right in your hand. And other more advanced ones actually have to be mounted in the cabinet with the routers and the switches. So they can be the size of a modem, and they can go in the part of the network where the modem would normally be found, but it does not perform modulation, demodulation. Firewalls, just a couple of notes here, they filter incoming and outgoing packets. They can be set to strip attachments, usually incoming, to prevent viruses, because that's still a major problem for us, even in today's networks, is people opening an attachment on an email and all of a sudden it's unleashed a virus or a worm on the network. We'll talk a little bit more about that in the antivirus video. Three popular ways to filter traffic on a firewall, and once you start working with firewalls, you'll see you can really tie it down to almost any value you want. But I've always filtered either by protocol, by source IP address, or by port number. And port number is very popular because that really lets you tie down what you're blocking or what you're allowing. Proxy servers. One main purpose is they are used to cache web pages for local users, and that makes web access a little quicker because the user is actually getting the web page from a local device on their network instead of having to go out to the web server and retrieve it. Now, if the proxy server doesn't have a copy of the particular web page, it'll go out and get it, send a copy to the requesting host, and then cache a copy of its own future use. Proxy servers can also be used to deny access to certain defined web pages. And I want to add something to this beyond what we talked about in the original lecture. You have to watch proxy server programs because a lot of them will have a lot of websites blocked by default, and that's not necessarily a bad thing. But sometimes with some of the wildcard characters they'll use, they'll block sites that you may not want blocked. And you'll find out about that very quickly from your end users. Because what happens is, with many proxy server programs, let's say that somebody is in their office and they want to go out to a legitimate business site, and it's being blocked by the proxy. Well, it goes out, hits the proxy server software looks it up and says, oh, this person, no one is supposed to be looking at, site, we'll just call it site X. So what happens is the user in their browser window is going to get something from the proxy server. And it's going to be a message, and it usually has the name of the software you're using. It says, access to this page has been restricted. So if the user is trying to get to a site they legitimately need to get to, they will call you, believe me. And then you can go in, and if they are supposed to be able to get to that, you can go in the software and add this page and say, okay, this page has been whitelisted or added. I want people to be able to get to the site. Now, if they're going somewhere they're not supposed to be going, and we'll just leave it at that, they're probably not going to call you. I had that happen once in many years of network support, and I was a little dumbfounded as to where the guy was telling. He just didn't know, and it was well, I can't name the site, but he just called me and said, well, I can't get to such and such site, and I just said, well, there's a reason for that, sir, and just left it at that. Proxy servers also have logs, so you can look in the logs and actually see who's trying to get to sites that they shouldn't be able to get to, and actually you can see the IP address of the host that is trying to get out somewhere they're not supposed to go. So that's what proxy servers are all about. Proxies can also run NAT, and remember we call that an intercepting proxy. So when you put all this access together, a proxy server really does serve as a type of firewall because you've got packet filtering, and that's what firewalls do. And we can set the proxy server to, deny or permit access to websites as we see fit. And also, when we're running NAT on a proxy server, we're cloaking the internal IP addresses. That actually happens with NAT period, whether you're running it on a router or a proxy server. The outside host cannot see your inside IP addresses, your network's IP addresses. So that's a little bit of security built in too. So again, a proxy server does serve as a type of firewall. Finally, transceivers. Little metal box fits right in the palm of your hand, and it is used to connect media that would not otherwise be able to work together. And mostly your experience with transceivers is going to be connecting a straight-through cable, cable with an RJ45 connector on the end, to an AUI port on a router, because that's going to be a DB15 port. It's waiting for a 15-pin connector, and believe me, an RJ45 does not have any pins at the end. So you've got to use a transceiver. You just take the RJ45, connect it to one end of the transceiver, and connect the other end of the transceiver directly to the router in question. So you'll definitely need transceivers. Your network probably has them. If you don't work with the routers and switches in your network, just ask someone who does, and they'll probably show you exactly what I'm talking about with a transceiver. So we got a lot of devices here that need to play nicely together, right, to make our network work. Sometimes it's a marvel that they work as well as they do with all these different devices. But mastering the basics of these is really the key, not only to exam success, but to a happy and healthy networking career. So that ties up the networking components video, and I'll see you on the next video.